We're looking at, for the first chapter, the Introduction to Random Variables, probability distribution. I'm going to call them tables, and they call them functions. It's just whatever they want to call them. So we're going to look at probability distribution tables or probability distribution functions. So let me show you an example of one. You take a situation where there is a number of things that could happen, and K could be 1, 2, 3, or 4. So I don't know if you've ever played with various dice, but there is a dice that only has 4 sides rather than the typical 6, right? And the way it works is that it's once you roll it, it looks like a little pyramid if you're interested. It looks like that. The number that's on the ground is the score, so you have to pick it up and look at it. But apart from that, it's fine. And probability X equals K just means probability, in this case, X will be the score on the dice, equals whatever K is, right? So imagine this little 1, 2, 3, 4-sided dice. Would it be reasonable to assume that each one of these is equally likely? That is an example of a probability distribution. You've written down all the things that could happen to that dice, and underneath it, all the possible probabilities. Now, there are a couple of properties that you use in some of these questions. So let's tell you the first one. What should all 4 of these add up to if it's a real probability distribution and you'd covered everything? They should always add up to the same thing. Agreed. Would you agree they should all add up to 1? Right? And the second thing is when you do a probability distribution, each one of these things has to be separate from the others. So you can only be a 1 or a 2. There's no overlap allowed, right? Which kind of makes sense, but we'll emphasize it, right? The fancy word is disjoint. It's a bit like mutually exclusive for 4 things, right? Nobody in any of these groups shares anything else with anybody else in that group. Pretty obvious when you've got 4 dice. However, using one of those properties, I can answer a question that looks like this. Let's have K and probability of X equals K, and you don't even need to know what K is. But I'm going to tell you this is 0.2, this is 0.1, this is 0.1, this is 0.3. And you should be able to figure out who that guy is. How would we find out what the final probability in this probability distribution table is?
Add up to 1.
Agreed. Add them up. And what's left then when you add them up? You add them up and what's left? I didn't quite catch it, but it might be connections that are causing trouble here.
It would be the answer.
Yeah. And the answer would be 0. What number?
7.
3.
Yeah.
3.
Yeah, 0.7, which leaves you with 0.3. Agreed? Right. So let's go and show you a couple of those questions and what they look like in homework.
That does not equal 1. It's 3, 4, 5, 6, 7. So the other one's 3. Oh, never mind. I thought you wrote down 7. Sorry.
Okay, we're good. Well, it's better to check than to let it slide and not notice a mistake I may have made. So let's show you what that looks like in your homework. It's pretty much what you'd expect. They give you a table and they ask you to fill in who's missing. So in this case, 2, 3, 4, 5, 6, 7. Very similar to mine. Would you agree that goes 0.3? Now up here, 1/7, 1/7, and 1/7. So what's left for the last one?
1/7.
Okay. So you will not overthink these questions. Will you take what is obvious is also what is correct? Would you agree they're pretty obvious what you need to do to find the missing number? Right. Would you agree in this question? It's add up what's there and whatever's left goes here. Now, let's use one of these completed ones now and do something else. Do you see this little guy here? That's mathematical for x less than or equal to 3, right? This story, x is the number of births in a day in a hospital. So in this hospital, no babies were born, happened about what, 10% of the time, right? And 5 babies were born, you know, assuming 5 separates, but it could be any combination like that happened about what, 5% of the time. So when they say this, what they're asking for is, what's the probability that it's 3 or less? Would you agree? 3 or less, x less than or equally. So 3 or less, wouldn't it represent all of those events? Now, what do you think you do then to get the probability of 3 or less? What do you do with those 4 numbers?
Add them up.
You add them up. So 52, 68, 78. There, nice and easy. Just add them up. Now, explain what that meant. Couldn't you describe it in this way? The probability that there will be 3 or fewer births.
Yes.
Right. Now, there are other ways of saying that, but that's the way they're picking it, so that's fine. Now, a little bit sneakier. What on earth is that in English? What probability are you finding when you find 1 minus
1.
x?
I want you to find the probability that it's not going to happen.
Correct. And what's the opposite of less than or 3 babies being born? What's the
More
opposite
than.
of that? More than 3, right? So I'm going through this list of trying to find more than 3. There we go. Would you agree it's that dot there?
Yes.
Why is it not the one underneath that almost looks the same? Because you're right, it is this one. It's that second last dot.
It
Why
cannot
is
be 3.
It can't be 3 because 3 is counted here, right? So the opposite would be bigger than 3. Next one, we are going to build a probability distribution for x, and what's x going to be? The number, or there we go. X is going to be the number of tails. Okay. So there are 8 things that can happen when you throw 3 coins. Here are the 8 combinations and they're all equally likely. So if someone says, what's the probability that x, the number of heads is 0? Well, isn't the number of heads being 0 the same thing as that guy?
1 out of
Correct. 1 out of 8.
8.
So here we go. 1 out of 8. Now, how about 1 head? Exactly 1 head. Oh, sorry, tails. Exactly 1 tail. Well, wouldn't that one count? That's 1 tail. Wouldn't that one count? That's a tail. Isn't that one a count? So would you agree that for exactly 1 of those, it's 3/8? If you do those guys, it's also 3/8. And lastly, what's the chances then that all 3 of them are tails? What's the probability of that happening?
1.
Are we cool with that?
Mhm.
Now, as a check, shouldn't they add up to 1?
Yeah.
And they do. Right. Question 5. Here is a probability distribution tree. Oops, I got a flicker there. And the sum of 2 values is as follows. Well, so this is a probability distribution. And they're asking you what's the probability that the sum, which is these numbers, is even. Well,
That's 3
1/9,
ninths.
3/9, and another 1/9.
5
What should we
ninths.
do to get that answer?
Add them.
Add them, and I believe that's 5/9. Are you happy where that came from? Couldn't I use that table to get the probability that they were even? That they were odd? That they were bigger than 4 or less than 5 or more than or equal to 4 or any kind of combination you like. Isn't it just a matter of looking at the table, finding out the things that you're interested in and adding them up, right? So if you're interested in odd, add up all the things that are odd. If you're interested in it being even, add up the probabilities of even things happening. If you want to know the chances that it's 5 or bigger, wouldn't you just add these two? Because aren't they the two things that are 5 or bigger? So if you have a probability distribution table, can't you just basically add them all up any way you like? Now, the next question, I'm going to go and do it on paper, but it's a story that I want to read it to you. It's going to have 6 left-handed kids and 14 right. So I'm writing that down for a second. 6 lefted, so 6L, and 14 right. Got that. Okay, written that down. And 2 children are going to be chosen at random. And the key word here is without replacement. Remember the without replacement thing. So you're going to choose two children without replacement. Okay, and X is going to be, the thing you're counting is the number of left-handed.
We can't see your paper.
Okay, you will in a few seconds. I'll finish writing that sentence and then I'll show you. Okay, let's show you the paper now. So I've taken that story and I've basically written down everything I need to create our guy. So here we go. I am going to create a probability tree. You need to create one of these because it's really the only practical way of coming up with these probabilities. And it's the without replacement that's basically screwing things up. So at each branch, the child can either be can be either left or right-handed. That's going to be the first child here. And this is going to be the second child here. Now, 20 kids, you're picking the first child. Out of those 20 kids, 6 of the 20 are left-handed and 14 out of the 20 are right-handed. You happy about those two probabilities? Right, 6 out of 20, 14 out of 20. Now, it gets a little bit more awkward now, I'll cover this up. The first child is left-handed. That means you've only got 19 kids to pick from. And because that child was left-handed, aren't there only 5 out of 19 left to pick? How many right-handed kids out of 19 do you have?
14.
14. Are you happy about that double split? Right, 5 are left, 14 are right. Now, if you do the bottom one, the first child is right-handed, so you still have 19 kids, but aren't 6 of them left-handed and the other 13 are right-handed? So what I've done is I've constructed the probability tree. Barbara, you look like you have a question.
Never mind. It was, I get it now. Never mind.
Okay, we're good. Now, each one of these 4 things is the destination. So we calculate them. And let's get the first one. It's going to be 6/20 times 5/19. And I'm going to do that on my calculator. And hopefully it'll work. So I'm going to go 6/20 times 5/19. And then hit the math button and do fraction. And it ends up being what? 3/38. Okay. The next one, 6/20 and 14. So 6/20 and 14/19. So 6/20 times 14/19. Hit the math button, choice 1 again, and I'm looking at 21.95. And the next one, 14 and 6. 14 20ths multiplied by 6 19ths. Horrible decimal turned into a fraction. 21 95s. And last but not least, which is this one, so it's going to be 14 20ths times 13 19ths. And now I'm looking at, hopefully a nice fraction, 91. 1/90. Are you comfortable about how I came up with those last 4 probabilities? Right. Now, what's that going to look like in the homework? Well, they don't get you to do a table, one of these trees. Do you know how in earlier homework they called this A and this B and this C, D, E, and you put the numbers next to it? What they do in this homework is a little bit different, but essentially it gets to the same thing. They ask you to find that guy. Well, a right-handed person is this number here. And then they ask you to do left and right, which is left and right, which is that one, and so on. Are you happy about how you could do those from the table? You just have to figure out which one of the 4 they're doing. Now we can construct our probability distribution table. K is going to represent how many, and X is left-handed. So 0 left-handed, funny way of counting it, 1 left-handed, or 2 left-handed. And we're going to get those from here. Let's see what we've got. What's the probability that you get 0 left-handed? Well, isn't 0 left-handed the same as right and right? So it's that guy. So 0 left-handed is that guy. Now, what about 1 left-handed? Well, wouldn't that be a right and a left? So it would be those people. But couldn't it also be a left and a right, which is those people? So what do you think I do to get the probability that I pick 1 left-handed person out of the 2? How will I get the number that goes there? You do.
You add them together.
Great. And then the last one, can you figure out, it's going to be 338. And as a check, shouldn't I add them and make sure it adds up to 1, which it does? Are we comfortable with that, that process? How you construct a probability distribution from picking 2 kids without replacement, left and right-handed. Let's, well, there's only one last question to do. I'm going to show you the question, then I'm going to return to this paper, because it's easier, I think, if you see what the question is before I start writing down all sorts of stuff. This last question, I do not need the probability tree for. Are you looking at question 7, guys? Okay, so a woman decides to have children until she has her first boy, or until she gets 4 kids. Whichever one comes first. So if she gets a girl, she stops, right? But if she doesn't, she's going to keep going to 4 kids. And if she hasn't got to be 4 kids, she stops. And the chance of a boy or a girl is 0.5, so they tell us that. And X, this time we're going to count X as how many children she's got. Did she have 1 child before she stopped? Was it 3 children before she stopped, and so on? Now, if you look at the sample space, she got a boy. Okay. Then she has a girl and a boy. You see, she had the first child was a girl, so she had to try again, and she got a boy, so that was it. She's happy. 2 girls and a boy. 3 girls and a boy. And what about this one? Well, she had 4 girls in a row and she gave up. My sister wanted a girl and she had 4 boys, so it's very similar to this. One of my sisters had that. So we are going to calculate all these probabilities that you see here, right? this list here. I'm going to show you how you do that. And then once we've done that, I'll return back here and start filling these guys in, right? So the first one that you're being asked to find is the probability that it's a boy. Well, one event, probability is a boy is 0.5. End of story. Now, down here, you're going to create your table. And K is going to be how many children in the family. Did you stop with 1, or with 2, or 3, or finally 4? So what's the probability that the number in the family is whatever K is? Now, what about the next one? Now, if you want to find the probability of a girl and then a boy, we make the assumption that these are independent. And since they are independent, you can use what's called the multiplication rule. And a girl is 0.5 and a boy is 0.5. So the answer here is 0.25. And the chances that she finishes with 2 children is 0.25 of the time. You happy about that? Right. Well, she had a girl. That wasn't what she was looking for. She had another girl. Still wasn't. But yeah, she finally got a boy. In a similar way to I did this, won't you be able to get that by simply just multiplying each one of them together? And that ends up being 0.125. Say again, Abby?
Oh, sorry. I didn't know I was unmuted.
Okay. So 0.125. Are you happy with that one? Now, let's see how this story finishes. She has a girl, a girl, a girl, and finally on the 4th kid, she got a boy. Or she had a girl, a girl, a girl, and she still ended up with a girl. In this one here, won't it be 0.5 4 times? Actually, won't both of them be 0.5 4 times? And each one of them is 0.0625, if you check it in your calculators. So how do I get the last one of the list? What's the probability that she finishes with 4 kids? Right, our family is finished at the end of 4 kids.
Add those 2 together.
Does that make sense? Now, if we did this correctly, shouldn't the whole thing add up to 1? And it does. Are we good? Any questions about these probability distribution tables? If you are comfortable with that, and there's only 7 questions, so it's a very short homework, I'm ready to move on. Last chance, any questions? Anything you want me to talk about? Okay. So I'll close this one off and get started on the next one. And with a bit of luck, we will finish chapter 8 today. It's only got 2 sections of homework in it. And we are going to look at a guy called the normal distribution. Well, we have done the normal distribution in the past, so we're going to kind of start from there and then add to it. But we're going to look at it from a population perspective. So you have a thing called the population mean.
I'm waiting for it to populate.
Okay, give it a chance then. I'll just keep talking and you can watch the video for anything that doesn't make sense. The Greek letter this correct this letter here is pronounced mu. So if you ever hear me say mu, I'm saying that guy. So you have a population and it has a mean, it's called mu. And a population can have a standard deviation. And we tend to use that Greek letter. And for those who can actually see that letter, how do you say it out loud? Starts with an S. Last chance. SI.
Sigma?
It is, it's sigma. Right, now, there's another guy that you've met. Can you remember the guy called the Z-score? Right. And the Z-score in very generic form has a formula that looks like this. It's the data, take away the mean, divided by the standard deviation. Well, if we want to calculate a Z-score and it's from a population, the data is going to be called X, the mean is mu, and the standard deviation is sigma. So you can see in some textbooks, that's the formula for the Z-score. It's the same formula as it's always been. Data, take away the mean, divided by standard deviation. So imagine I have a population whose mean is 100, whose standard deviation sigma is 11, and I would like to get the Z-score for 123. Then to get the Z-score, you do X, take away the mean, divided by the standard deviation. So you do 123, take away 100, and you divide it by 11. And then you go to your calculator, and you do a bracket, 123, take away 100, close the brackets, divided by 11. Why did I put brackets around the top? What was my reason for doing that?
So that the calculator doesn't do 100 divided by 11 first.
Right, to get the order correct.
Because
So-
PEMDAS.
Because of PEMDAS. So to 2 decimal places, unless the question says otherwise, let's assume that all answers are to 2 decimal places. The Z-score is 2.08. So are you comfortable about a population mean is called mu and a population standard deviation is just given the name sigma? So if somebody says to you sigma is 10, don't you know they're talking about a population standard deviation and it's 10? And if they say mu is 1,000, aren't you talking about a population whose mean is 1,000? So the Greek letters allow us to identify whether it's a sample of just a couple of hundred people or whether it's a population, which means everybody, right? A census, essentially. Right, do another Z-score. Suppose I have a mean of 50, sigma, a standard deviation of 5, and I want to find the Z-score for 43. So Z-score, data, take away mean, divided by standard deviation. 43, take away 50, divided by 5. And that ends up being negative 1.4. Isn't it okay to have negative Z-scores? And positive Z-scores as well, obviously. Now, suppose I do a calculation and I get a Z-score of 4.12, just for argument's sake. Why can I say that that particular score that generated this Z-score will be considered an outlier?
Because it's outside 3 standard deviations, like the rule is -3 to +3.
You nailed it, that's it. Remember, we probably said it more like English, right? If plus or 3 standard deviations away from the mean is an outlier. Remember that phrase? Plus or minus 3 standard deviations away from the mean. Do you know the Z-score, these numbers? They're just telling you exactly how many standard deviations away from the mean you are. So this one here is just what, a little bit over 2 standard deviations away from the mean. And wouldn't this be about 1.4 less standard deviations than me, right? So going to the left, the smaller side. Are we okay with calculating z-scores? Can we call that done? Right, so as long as I tell you these three guys, you're comfortable with getting this guy. Okay, so next thing is I'm going to have to load it up, of course, because it got killed when my computer died. Where am I going? Going here, going here. Right, that's a lot. And make sure I get the questions. Almost here. And yeah, okay. Right, so what we've just done right now is only going to get you by questions 1 and 2. Right? You know, it's something. Right, so findings. Next thing I'm going to show you is a guy called the normal distribution. If you get a distribution, right, let's say it's the ages of people or the height of people in a whole population, and you plot them, you will very often get a nice bell shape. Great. You remember that guy? And that is called a symmetric distribution, but it's also called a normal distribution. So we're going to call it a normal distribution. And it has some very interesting properties that we've met some of them before. For instance, right in the middle, won't that be the mean? Agreed? So whatever, if that was heights, that would be the average height of people, right? If that was weight, that would be the average weight. If it was IQs, it'd be IQs. And we're going to call that guy mu, because he's a population mean, right? So we're dealing with that. And then you'd go, what, 1, 2, 3 standard deviations, 1, 2, 3. Remember the 68, 95, 99.7 rule, that guy. So we have met this shape before. But here's something new. Suppose we put some numbers on this. So suppose it's an IQ story. And the average IQ of Americans is 100. And the standard deviation is 15. So this would be 115, this would be 130, this would be 145, and this would be 85, this would be 70, and this would be 55. So I'm just putting some meat on that. Suppose I want to know this. Right there is 120. And I would like to know the probability that you choose somebody from the population and their IQ, which we'll call X, is greater than or equal to 120. Wouldn't it be nice if we could find that answer? Essentially, what percentage of people have an IQ bigger than or less than or between any two numbers, right? And SALT is going to be how we will do that, right? So when you go into SALT, we'll show you in a few minutes because I've got the thing set up now. We are going to have to know some things. We need to know what mu is, right? You have to tell me mu. You'll also have to tell me sigma. And then you will have to tell me what you want. So you might want to know the probability that X is greater than or 120, great? Maybe you want to know X is less than or equal to 111. Or maybe you want to know what's the chances that you get an IQ between 90 and 121. These are the 3 typical probabilities that you want to get from one of these distributions. So if you think of X as being IQ, what's the chance that you find a person whose IQ is bigger than 120? What's the chance that you randomly pick someone and their IQ is less than 111? Or what's the chances that you get an IQ between 90 and 121 in this case? Now, once you know how to use SALT, It's actually very quick because it does pretty much everything for you. So I'm now going to go and set up a question and show you how you would use Solve to do it. Right, and don't worry about the particular question that they've got here. I'm just going to use the one I've got instead, right? So you, probably too much. You hit the sort button. And again, I'm going to have to shrink this down a little bit. There. Go. I've got windows open everywhere. Right. Can you see the heading? It's under distribution calculations. So make sure you're there and you'll see a picture that looks like this. Depends on what your last question was. Here, make sure it's a normal distribution. Put in the mean. In this case, the mean is 100. Put in the standard deviation. In this case, it's 15. And the first question I wanted was X greater than or equal to 120, right? I wanted to know IQ's bigger than 120. So if you want a bigger than, pick the right tail. You see it shading to the right? And you tell it what number you want it to be bigger than and 120. Do you see that guy is almost the way the question would be written in the textbook, right? And you see a little graph to help you out, show you a little picture of what it is. And the answer you're looking for is that one. So it would be what, 0.09121. Now, won't you use that for bigger than 50, bigger than 55, bigger than anything? The minute is X greater than or equal to a number, right tail, right? Right tail is for bigger. The second question I've written down was less than 111. Which one of these guys are you going to do for the less than story?
Left tail.
Agreed? Left tail. And it's 111, so you just need to go here and change that to 111. And can you see a little visual? Looks good. And the answer is right underneath. So in this question, the chances that you get an IQ less than or equal to 111 is 0.76832. Now, the third one I had was a between, right? A between 90 and 121, right? 90 and 121. Which one of those is going to get me that probability? I want a between. Mm-hmm. I'm glad I phrased it that way because it helps you pick it, doesn't it? And we want to be on one side, 90. That was the question I chose, 90. And on the other side, we would like, what was it, 121.
Backwards.
And what was that about backwards? Eric, you said something?
Never mind.
We're good. And what we have here is the answer, which is 0.66675. Of course, you're probably going to round some of these off to 2 or 3 decimal places, but I've put in all their values. Are we good so far? Any questions? We cool? Right, let me just return for a few seconds back to what my whiteboard looks like. Can you see that in the homework, you just get the question and then there'll be a box and you put in the answer. Pretty much everything else is done for you in Solve. So can you imagine they'll have a question that looks like this and there'll be a box. Maybe you round it off, maybe not. Are we cool? Now, there is a very special normal distribution, which is called the standard normal distribution. And it's essentially the same as that guy. It's got all the same properties. But what is the mean and the standard deviation for a standard normal distribution?
One.
Okay, which one of these is 1? because one is an answer for one of the two.
The mean?
Standard deviation is one. And what's the mean?
Would that be 0?
Yes. Do you know if you take a whole set of data and you turn them all into z-scores, you know, those z-score things, you end up with a standard normal distribution and it doesn't care what the units are. And the mean will always be 0 and the standard deviation will be 1. So if you get a question that looks like this, it might look a little bit, oh, darn it in space. So do a few on this. Okay. It might look just a little bit different. Do you notice that they don't use X? They sometimes use Z. Does it matter? Nope. It's just a lettering. Z is typically used for z-scores, right? And aren't z-scores members of the standard normal distribution, right? That's how they're calculated. So let me show you, if I can. This guy. Put him here. And let's do what's the chances of the probability that you get z-score less than 0.3? Right. Are you looking at normal distribution?
Yep.
You see the mean is 0 and the standard deviation is 1, which is actually what you normally start with. In this case, I don't need to change it because that's what it is. And I wanted z less than 0.3. Oh, less than, happy with the left tail? Less than. Oh, that's a good way of remembering. Left, less than, right? L and L. Left, less than. And 0.3, I think, is the number we just chose. And the answer would be 0.61791. Suppose I wanted to know bigger than 1.9. Wouldn't I do a right tail and change this to 1.9? Suppose I wanted to know a z-score between 0.1 and 0.7. Between 0.1 and 0.7. And the answer is the guy underneath. Do you feel comfortable about how you can use SALT to do all these probabilities of getting bigger than or less than something? Are we good? Jumping around as I do. Let's go back to the whiteboard for a minute and create a story. Let's suppose that we have a population of Scottish people. And for an adult, the average height is 65 and that the standard deviation is 6 inches. And I would like to know what's the probability that you get a normal person and they are greater than or equal to 72 inches. In other words, what's the chances that you pick a Scottish adult and they're bigger than 6 foot tall? Are we cool on that? And that's going to be question 1. Now in question 2, there's a second country whose average height is 67 and whose standard deviation is 2. And we're going to calculate what's the probability that you get a person from this second country who's also 6 feet or taller. So before we use SALT to actually put numbers on these, do you think that these are going to be equal? Or do you think one of them and which one is going to be bigger? What's your gut feeling? Which one is more likely to have 6 foot tall people? Country 1, country 2, are they both about the same?
Probably country 1.
Okay. Any particular reason? Does it just feel like it might be?
Because the standard deviation is bigger.
Ah, I like your thinking. And so when a standard deviation is bigger, doesn't that allow a lot more variation? And a lot more variation could well mean, as I think it will do in this case, that there's a better chance of getting that 6 foot tall person, right? Even although the average is 65, the variation is so big that there might be more people in that height group, which seems a contradiction, but it's not. So let's put it to the test. I am looking at this fella, and we'll do country 1 first. Mean is 65. Standard deviation is 6. And we want bigger than, so it's a right tail, and we want bigger than 72 inches. And I'm just going to round this off to 2 decimal places. So there's about a 12% chance that a person from the first country is bigger than 6 foot, right? 12% chance. Let's look at the second country. Now, their average height is a little bit taller, but their standard deviation is quite small. And the chances that you get someone greater than or equal to 72 inches ends up being 0.00. Okay, I'll have to go 3 decimal places. Or if I round it off, I guess. There we go. Wow. That is interesting, I think. When you look at the comparison then, do you see why standard deviation is important if you want to distinguish between 2 groups? If you just looked at the means, wouldn't you say this country has taller people? Which it does on average. But if you look at really tall people, let's say 6 foot or taller is really tall people, doesn't this country have quite a lot of people who are in that bracket? And doesn't this country almost have nobody? So you might think, how can both of those things be true at the same time? How can your average be bigger, right? Yet you have fewer 6 foot people. How can that happen? You're 2 inches average height better than the first country, but you've almost got nobody who's 6 feet tall or bigger. What kind of population are you looking at? Aren't you looking at people who are all about the same height? The variation, right? That's this guy, is tiny. Isn't there a lot more variation? Now, do you know what else you'll get in this country? Won't you get an awful lot of very small people? And won't that balance the very tall people? That's why the average can still be less. So I think a good lesson was came out of that question. So moving my windows around because I'm confused. And let's try some questions then. Show you what they look like in the, gone to them all the time. Let's have a look at what they look like in the textbook. Right. For each value of Z star, find the cumulative probability that Z is less than Z star. You know, you could have ignored that entire sentence and just focused on there. And Z star is going to get replaced by 1.96, negative 2.33, 2.58, and then finally 1.65. So I'm going to just write down a couple. I'm going to do the 1.96 and the negative 2.33. And we are basically being asked to find what's the probability that Z is less than 1.96. So let's do that. Kick in here. Bring this over. In this particular, darn, I forgot the question. Oh, it's a standard normal because they're using Zs. Okay, now I know. How did I know it was standard normal? Because they use Zs. So if you ever see a Z, you know the mean is nothing and standard deviation is 1. And we are looking for a 1.96. So a less than 1.96. And the answer is what about? There we go. Would you agree it's about 2.5%, 0.025? How about negative 2.33? Negative 2.33. Nobody noticed what I forgot to do. Are we finding less than right now? Aren't we finding more than? Shouldn't have done this guy. Negative 2.33. There we go. So, wow, look, isn't that tiny? 0.0099. What about less than the first number again then? What about less than 1.96? This time it's the correct answer. Yeah, does that look like 97, 98% of everybody's going to have a Z score less than that? If they'd asked you for a between, let's say between -1 and +1, shouldn't that answer be around about 68%? Remember the 68 rule? Well, isn't that number there pretty close to 68%? One standard deviation. Right, how much is 2 standard deviations away? Can you remember that number?
95.
Okay, so if I do -2 to +2, won't that represent 2 standard deviations away from the mean? And does that number there look like 95%, roughly? 0.95, 95%. The hardest one of the 3 to remember is, what is 3 standard deviations away from the mean?
99.3.
Darn close, 99.7. Let's find out. Can you see 99 and a 7? If you round it off, it is 99.7. So do you know that 68, 95, 99.7 rule? Can you see where the numbers came from now? 1 standard deviation is 68, 2 is 95, 3 is 99.7. Right, I'll skip that one. Right. If you see an X, won't there be somewhere in the story a mean and a standard deviation to use? If you just see a Z, what the assumption is there, isn't that mean it's a 0 mean and a 1 standard deviation? Because Z means it's a standard normal distribution. Z's again. And X's. Let's do this one. Find the following probabilities. This is to do with pulse rates of adult females. Their mean is about 77 and their standard deviation is 8. So I'll write that down, 77 and 8. And we want to know what is the chances that you choose someone at random and they're less than 73. So here we go. For pulse rates, the mean is 77. The standard deviation is 8. And we want to know less than 73. Less left tail. 73. And the answer is that guy. And they want the answer to 4 decimal places, so don't I drop a digit to keep it happy. Are you comfortable with using salt to get these bigger than, less than, in betweens? I got a thumbs up. We feel good about that. Just keep practicing. Okay. Okay, these ones just have words attached to them, but it doesn't really change too much. Suppose that the amount a student at college spend on textbooks varies, and it's a normal curve, right? And the mean is $450. So on average, a student spends $450, and that the standard deviation is 150. What's the probability that a student will spend less than 585? So it'd be the probability that X is less than 585. Great. 585 it is. I'll hit salt. And we'll calculate that probability pretty quickly. The mean of these textbooks is $450. The standard deviation was 150. Quite a lot of variation in the price. And we want to know less than 585. And there's your answer. So we would be putting in that guy. Did it have a decimal place? 4 decimal places. So I'll round that off. There we go. And that's the only bit you would have, right? You'd only put the answer. So as long as I know that it's roughly symmetric, right, normal in shape, if you tell me the mean and standard deviation, can I find the percentage of anything, right? Percentage bigger than this, less than that, or betweens? You can do, it's pretty powerful that you can do so much. Any questions? We still good? Okay. Another word story. Suppose the year, maybe I can make this bigger. Don't know. Let's try. Suppose the yearly rainfall for some city is normal. The mean is going to be 21 inches, which that was us. And the standard deviation is 10. Oh, God. If that was true, wouldn't that be a place where you could get almost any amount of rain? Couldn't you get as much as 50 and none, right? You could have a year where it was a drought. So that's not very pleasant. And they want less than 11. So go in here, start with my salt. The mean is 21. Standard deviation is 10. And you want a less than. And we want to be less than, we want 11 inches. And so our answer would be that number. If you want between 15 and 26, I've lost one of my guys, 15 to 26, there we go. If you want between, well, put in the mean again, different question, 21, 10. If you want between 15 and 26, I better shrink this up so I can see it. Between 15, 26, you're going to get about 41%, which is that number. And to 4 decimal places, we'll lose a digit. Apart from the story finishing, isn't this, here's a mean, here's a standard deviation, find it bigger than find, you know, the probability it's bigger than a number, less than a number, or between a number. Isn't every one of those stories so far, in general, been that process? So it's nice when, I think the last week's work was very bitty, wasn't it, all over the place and lots of different things going on. Would you agree that this chapter 8 has been much cleaner, right? You got a theme that you can get your teeth into, at least I think. Okay, I got to pick one last one, so why don't we do this? Did you know that the total cholesterol level of women in that age group is normally distributed and that their mean is 203 and that their standard deviation is 35. Oh, yeah. And now they are making things sneaky. And let me check if they've done that before this one. No, this is the only one that you need to do, so I'm glad I chose it. We are going to use salt in a different way. Find the cholesterol value such that 24% of the women, right, in this age group have a lower cholesterol. Now, what on earth does that look like? 24% lower. Let's show you. Okay, bring it over here. Normal distribution, 203. Standard deviation, 35. Less than. But they are not telling us this number and asking us to find the probability. They're actually telling us the answer, 24. And there's the number. You see, you can put the percentage in and it'll tell you the value. So it works both ways. And so that guy, if I can copy it. Goes there. And what do they want? Oh, they want 2 decimal places. So 279 becomes 28. I think that's the only time. There might be another one and I missed it. Now, they call that a percentile. And the percentile is called the 24th percentile. So that's really not a question. Oh, so I can use this table, right? Can I use it the other way around? I can tell you what score you need to do to be in the top 10%. Do you want to be in the top 10%? Let's find out what your score is. Somebody give me a test. What average is this test? Give me a number. I need to know an average.
84.
Okay, so we had a class test and the average was 84. And you want to be in the top 10%, don't you? Right? So give me a number less than 5 for the standard deviation.
3.
3. So we are going to find out what score do you need to do in a test to be in the top 10% if the mean is 84 and the standard deviation is 3. So are you looking at salt right now? Because I'm not sure where we are. Okay, so we go here and we'll put in the average for the test is 84. And we'll put in that the standard deviation is 3. And you want to be in the top, so don't you want that number there, right? Okay, now, if you're in the top 10%, don't you have to make that guy 0.10? And what do you need to get? You need to get about what, 88 in the test? 87.8, count it, you know, round it off. That is so powerful, isn't it? That all you need is a mean and standard deviation, and look at all the cool things you can get. You know, what percentage of people get an IQ bigger than 120? What get an IQ less than 90? What's the IQ between two numbers? What do I need to get to be in the top 10% or the bottom 5%? You know, I can even answer questions like that. And we have lucked out here, everyone, because we did not lose power. Well, again. So will you lot say hi? And last name, I should say. So we take attendance. And I will hang about for any questions, if you have any.
Thank you.
You're welcome. I'm still trying to close windows here, but I think I've got all the windows I need to close. Any questions?
I had a question
Yes, Harper.
from the email that I sent you
Yes.
yesterday. The one about the numbers with the beginning number, like the 3 would be the three numbers from 000 to 999.
Yes,
Right. So my question was, isn't 0 not an odd number or an even number?
it is considered an even number in mathematics.
Oh, okay.
Right. Even numbers, I know 2, 4, 6 are even, but
Right.
the formal definition of an even number is you can write it as 2 times something. So 2
Okay.
times nothing counts. So 2 times 1, 2 times 2, but 2
Okay.
times 0 counts.
Okay. That makes sense. Because I was like, what does 0's not an even number? So I wasn't counting it. So my numbers.
And so your numbers were wrong.
Yes.
Gotcha.
So, okay.
But you won't do that again, right?
No,
So
no,
we've learned something.
I was cursing at my
Oh,
computer.
That is not very ladylike, Abra.
I live with a sailor and I have a sailor's mouth.
Did you work in the Navy? Yes.
No, my husband has been in the Navy for 16
So
years.
it's his fault then.
It's his fault. Yes.
Okay.
So anyways, okay, perfect. Thank you for answering that question for me.
No problem. Any other questions, guys, before we call it a day? Eric, are you falling asleep or are you waiting for a question?
I was just sitting here.
Okay. Alec, you got a question? Isabel? Anybody?
I got one.
Okay, go for it.
Yeah.
What you got?
Well, it was the one about the probability of having 2 boys, and they wanted to know the probability of having one of each.
Right. So what you needed to
I think the
do,
number
keep going.
was 525. I think my number was.
Okay. Did they give you a decimal for the chance of getting a boy? Because they're not always
Yeah.
0.5. So it would be 0.what in your story?
It was 0.525.
Okay. So that makes it 0.475 for the girl. Agreed? Right. So you want one of each. There are 2 ways in which you can get one boy and one girl. Boy first, girl was second, then you get a girl first and a boy was second. They count as different events, but they also count as one boy and one girl, right? One of each. Now you want this one, it's a probability of a boy multiplied by the probability of a girl. And these are independent. So if you get a boy, the chances that you get a boy or a girl, the next child, has nothing to do with what happened previously. So because of that, we can use a multiplication rule, which essentially says you can multiply them together. Now, if you do this one, it's a girl first, multiplied by a boy second, and you end up with a very similar looking multiplication. In fact, isn't it really just the same 2 numbers, but in reverse order? So I'm going to find just the top one, 0.525 times 0.475. And I don't know what they wanted it rounded off to, but hopefully they wanted it rounded off to something. So what did they say? Is that 5 decimal places? Okay, so 0.4, 2494 then, right? And can we assume that this is the same number, so we get that? So far, so good. So the probability that you get one of each is actually this and this. So don't you just add them together?
I think that's the part I struggled on.
So I'm doing that. Well, adding is the same as doubling, so I'll just do that. If they're the same thing, adding is the same as doubling. And I got that guy. So it's slightly less than 50% chance that you get one of each. Now, if they said, what's the chances that both were boys, wouldn't you do that guy times itself? And the chances that both of them were girls, you do this number times itself. And that would get you the other opportunities of what could happen. Okay, does that answer your question, Eric?
Yes.
Yeah.
Thank
So
you.
if you figured out where you went wrong, right, well, we've cured the problem. I like curing problems. Any other
I can go back
questions?
to that.
You're welcome. Any other questions? last chance. If there's no more questions, I am out of here.
Can you go over the mutual exclusive and not mutually exclusive again for me, please?
Sure. Right. I'll write them down full ones, mutually. Mutually exclusive, which I like to call ME for short. Two events, A and B, are mutually exclusive if the probability of A given B is 0. That's essentially the test for it, right? So the probability that A happens given that B happens is 0. That is how one way you can test two things are mutually exclusive. In English, what does mutually exclusive look like? Well, A and B have no common terms. So if I said to you A was hearts and that B was clubs, would you agree that they don't share anything in common? There is no card in the hearts that's also a club and vice versa. So these would be mutually exclusive. Other situations. A is being a boy, B is being a girl. We would consider them mutually exclusive biologically, right? I can't think of any.
Could you do that with like a fraction? Because I struggled on that as well.
So what do you mean by a fraction?
So one of the questions was like A given B is like 1/6 and A equals 1/2 and
right.
B
So A
equals
equals a half. Say B equals a third. You know, something like that, right?
yes.
Now,
yes.
if you get the probability of A equals B equaling, who cares what it is? Let's say it's a sixth, just for argument's sake. If the probability of A given B is a sixth, then A and B are not mutually exclusive. They must have something that's connecting them. And you say, well, how do I know that? This test has two sides to it. If you're equal to 0, you're mutually exclusive. But if you're not equal to 0, you're not mutually exclusive. So I can tell, if you tell me this, if you give me this fraction, I can tell you that they're not mutually exclusive. Does that help?
Yes.
Right, now, there's another one that looks very like it, and people very often get confused between the two, but they are different. Two events, A and B, are independent. If the probability of A given B is the same thing as the probability of A, and they are not independent, also called dependent. It's another name for it. If the probability of A given B is not equal to the probability of A. So this is the way you can do it with numbers. So back to this story. Do you see how probability of A was a half and probability of B was a third? And I told you that the probability of A given B was a sixth. You see this one here? What can I tell you? Well, the probability of A given B is a sixth. The probability of A, because you were told, is a half. Are they equal? Obviously not. What does that tell me? It tells me that A and B are not independent.
Oh, okay. Get it.
Now, in English, Independence means the one event has no effect on the probability of the other event. So we talk about you having 2 kids and getting a boy or a girl for your first child has no effect on your chance of getting another boy or another girl in your second. So in that situation, when they are independent, we can use the multiplication rule, right? P of A times P of B.
Thank you.